I've got all this sorted out. There's my channel. Am I live? I always love the preamble. I'm sure people have got such better ways of setting these things up than I do. But upcoming, there we go. Upcoming. I don't want to be upcoming. I want to be live now. What's going on? Okay, good. I hear that. See that? I see my chat. I see my Twitch. Where is my fabulous Twitch? There we go. Okay. All right. Let's get I'm live. Apparently I am live, which is great. Okay, fantastic. All right, we are live. It is time for some I'm with Genius, and I am again incredibly excited to be joining you today. Feeling very, very fortunate. How is everybody? Can everyone hear me all right? Paranoid Badger, how do you hear me? Or Matt W. or Casually Sandra. Howdy to you all. Hello, Mittens. Okay. This is the plan for today, as you probably already know. We're going to be talking quantum physics with my new favorite person, Lisa Verner. You are going to love this because I'm very lucky. I get to have these little pre-chats with people first, just to make sure that you know they're comfortable with this whole sort of chatty format and they understand just what a bag of squirrels it is talking to me. I came away so excited about this stuff. And I'm feeling incredibly fortunate at the fact that I get to, having played geniuses on television, I now get to pester the real ones about the real science and what's going on. And Lisa has got so much great stuff to talk about. And I'm going to do my best to embarrass her first before I bring her on. Without further ado, why don't I invite Lisa to the chat, let her know that she's coming in. Here we go, Lisa. Now I will unmute you, as I said I would. There you go. How does that sound, everyone?
Hi, it's so great being here. And yes, now that you set the expectations that high, I'm here to disappoint everybody. So that's a good starting point.
That's my job. My job is to disappoint. Yeah, it's like, all right. Let's just double check, make sure everyone can hear everyone. Okay, sounds good, fantastic, good. Then we've got lots and lots to talk about. Lisa, first off, thank you so much for this, for humoring me.
Thank you. So as you said, this pre-talk was amazing. I really loved it. I love this opportunity. I'm so happy to be here, and I hope I can give you an insight into what it is that quantum mechanics and quantum technology can be.
Wow.
And to excite a whole new generation to go into this and help us solve all the challenges on the way and everything and make this world a better place.
So, that's amazing. So maybe first thing I should say is what do you do? What is your job? What is your, how do you find yourself in this quantum entanglement?
Oh yeah, so my life story is a bit of a complicated one. Things happen and I moved around a bit. So I got to learn about different kinds of physics, such as plasma physics and high energy physics. And I did a whole lot of different things before I found myself be really, really intrigued. And coming back to my note before, so it's never too late to come into quantum physics. If you later in life decide that that's what you want to go, please go for it.
Even me?
And then I ventured a little bit around Europe. Even you, of course, if you want to, you're most welcome. Come by, we'll educate you and we'll set you in front of an experiment and you get to play with it a bit and experience what it means firsthand and be very confused by it. And as soon as you reach that level of confusion, we know that we're doing it right, and then you take it from there.
Sorry, I interrupted. Carry on.
No worries. So eventually I found myself at the German Aerospace Center, and they were sort of recognizing the huge potential that is quantum technology and the actual step right now that we are in it and in sort of the transition from quantum mechanics to something that is actually a technology that could be bought in stores or could be, introduced into cars and planes and ships and stuff. And to just see how the application would work, they founded new institutes. And as such, I found myself at an institute which was called the Institute for Quantum Technologies in Ulm. And then finally, right now, I am at the institute, the DLRs, the German Aerospace Center, the DLR Institute for Satellite Geodesy and Inertial Sensing in Hanover. And we're trying to do our best to develop the next generation inertial sensors based in our case, cold atom systems. And I guess we're going to get into what that means and what that is.
Because this is wild. Yeah.
And the other side to that is actually almost as important. So the satellite geodesy talks about climate change and how we can apply quantum technologies to there are three things: to monitor, fight, and protect people from the effects of climate change, which I've christened green quantum to, give it a bit of a catchy word.
Oh, nice.
Yeah.
But
that is something that is also very near and dear to me, to make sure that we can not only develop the technology, but also apply it to something that is a benefit for society, I want to say. I know these sound very honorable and maybe a little too honorable for what we're doing, but here we are.
Well, it's funny, though, because, I had no idea until fairly recently that this wasn't just a type of physics. I didn't realize we were actually using it in monitors and using it I didn't realize that MRI was all about, the quantum world. So it's just amazing that as hard as it is to get your head around this stuff, it's being put to practical use. So it's not like it's not imaginary. So,
It's not imaginary, and a lot of the things we use are very dependent on quantum mechanics. And the fun thing is what I'm trying to avoid is to think about where it stops, because then down the line you can argue that anything is quantum mechanics, and then it sort of becomes very meaningless. But there are some life. I could argue that life only works because of quantum mechanics, because of tunneling effects in the brain that allow electrons to move, and
there was a new study about that, about the tryptophan molecules in tubules, and they're thinking it creates quantum quantum properties, quantum something or other.
Yeah, so it's the tunneling effect, which basically means if you the easiest way to think about it is if you pour water into a glass, quantum mechanics would allow you to take a water molecule out of that glass without actually moving it above the water, but above the glass surface, but simply for it to tunnel through the barrier. This is a very fundamental property of quantum mechanics. Everything in quantum mechanics is described by a probability, and as such, a water molecule, if we want to stay in that very analogy, a water molecule is not only the water molecule that you would see or think about in a very classical sense, maybe as a ball, which then contains of protons and electrons and stuff, but you would probably think of it as a small ball that is somewhere, and it's very physical, and there it is, as the table is,
like the rest of the world.
My laptop is, like the rest of the world. Yeah. Turns out none of the world is like that. So it's like the rest of the world, but in a very different way. And so quantum mechanics tells us that this ball can also be described as a wave. Right. This is the fundamental property of quantum mechanics, that everything you have can be described as a wave or as a particle, the so-called wave-particle duality. And if this sounds unintuitive, then your brain works perfectly well.
Then we've got it.
No, you've got it.
You got it, yeah. You don't understand? You got it. Yeah.
Perfect. You got it. You're on a good track. This is what it is.
Right.
It's not magic.
Right.
It's not magic. There's nothing. We have all the math, or part of the math. Some of the math gets too complicated for it to actually write it down and calculate the end of the equation. We use some approximations and stuff, but in the end, we have a theoretical understanding of what is happening, and it's still that the actual phenomena baffles me.
Because it's completely unintuitive. It doesn't make any sense.
It's completely unintuitive.
I pour water in a glass,
doesn't make any
it goes
sense.
into the glass. It doesn't go through the glass.
Yes.
I mean, unless you've got a really terrible glass. But you're saying it does.
And quantum mechanics tells you it does. There's a finite probability, so a probability that is different from zero, for the water molecule to be outside of the glass, and this is the tunneling, because you have a barrier that you cannot overcome. In principle, the glass, the side of the water glass, and for the particle, it's possible to go through. And with that, the thing that you sort of alluded to, the biology, chemistry, all of these kind of things. There's quantum biology, quantum chemistry. All of this is possible because of this tunneling effect, which then enables thought. At least there is some studies that suggest that, yes, our brain work because quantum mechanics allows for tunneling.
But we used to think our brain was too sort of warm and squishy, and they were too big to affect it, right? Isn't that what they're originally?
Yes, and that is still true for it as a whole. But if you're looking really down and you want to see how particles interact, and you are going down to the level of an individual electron or individual photon, or you want to transmit an information of sorts, then you come to a point where the warmth of the environment doesn't really affect it that much.
Okay, right. Okay.
Yeah, this will come back if we're talking about very precise measurements, or if we're talking about actually wanting to observe quantum mechanical phenomena. Then we very quickly come to a point where temperature is something that is going to inhibit that.
Right. This is where your satellite stuff comes in.
Yes, where the satellite stuff comes in, where if you want to study the limits of quantum mechanics, if you really want to understand, so because you said the world around us is very deterministic, right? So there's the table in front of me, and I do never ever experience that table in front of me to be a wave and to suddenly not be there anymore.
Right.
I think there's some animations where somebody goes out the door, closes the door behind them, and then the table flies out of the window. Going to the Schrödinger's cat example, where you don't know whether the table is there or not as long as you don't see it.
Right.
And that is, again, very unintuitive for us. But we experience it this way. So the table is there, and we're pretty sure that it's still there. And we also don't understand that there is a finite probability for the table to not be there. So there has to be sort of a barrier between, or a point, a limit of quantum mechanics, where at least the effects are not felt anymore or seen anymore in that.
And what is that called? That's the quantum barrier, or the what do we call that?
You would just talk about the limit of quantum mechanics,
and
it's a fun idea to think about that, because it's a lot of people, or like in the very general sense, people think of quantum to be very small, and that is not true. There are different ways of looking into the limits of quantum mechanics. One way is to use entangled photons, and we have performed experiments over several thousands of kilometers and still found that quantum mechanics is valid. So
explain entanglement to me again, just so I've got a...
Sure.
Was that a trick question? I mean, I get the premise of it, but my hunch is there's probably a lot more to it than what I've got.
Yeah. So entanglement, again, it is very unintuitive, and we have
to start with it always has to start with that. I have to
start with that, yeah. Because I've experienced people looking at me like,
what?
No, this can't be true, and I'm like, yes, no, it's. Of course you can conceive it. It's difficult, it's different.
Right.
Stick with me. So it's usually used in photons. And Einstein called it the spooky interaction at distance. And what it does is, in photons it's best explained by polarization. And polarization is something that you have probably experienced if you go to the cinema and you go to one of these 3D cinemas, and you get these glasses that one of them has vertical stripes and the other one has horizontal stripes, and if you put them over each other, you can basically black out the light. This is polarization. So you have basically vertically polarized photons, and you've got horizontally polarized photons.
And a lot of broken 3D glasses because you've been playing with them.
Yes, I've been playing with them. It's fun. It's a lot of fun. At some point, I bought the plates themselves just to have the fun.
Oh, really?
Yes.
Oh, wow. Okay.
Yeah. Oh, you can do so much fun things with them, but we don't. This gets. If I don't have them here with me, that's probably too difficult.
We'll do that next time. Okay, great.
We'll do that next time. Anyway, it's important to understand that there's sort of a coordinate system in which you can give any photon polarization some value on the horizontal and the vertical polarization axis. And so what you do is, you take an unpolarized photon and you send it through a crystal. And this crystal produces, from that one photon, produces two photons. That is so far so easy. We can call that a beam splitter. That works. You just split the energy. That's all perfectly fine and normal. And now you think about the probability of this photon being vertically or horizontally polarized. And if you look at these probabilities, there is sort of an overlap between the two, where the photon has an equal probability, the emerging photons have equal probability of being vertically or horizontally polarized,
Okay.
which means by now I know that the overall state is unpolarized. And I know that one of them has to be polarized that way and the other one has to be polarized this way. But I don't know which one is which. And it's even worse, the photons themselves don't know. So they are not defined in a state. They have a 50%, each of them has a 50% probability of being vertically or horizontally polarized.
Wow.
And now you send them out, all right? And here comes the Schrödinger's cat again, as long as you don't observe any of them, they remain sort of connected to one another by the wave function. There's no actual physical connection, but there's the overarching wave function. You can separate them out. And that's what is called the entanglement, this sort of connection between the two.
Right.
And once you measure them, the other one has to be the other thing. So if you measure one of them to be vertically polarized, the other one has to be horizontally polarized. But that only happens in the moment that you're looking at them.
Right.
And I know that this sounds wrong.
Yeah,
I know
like
that it sounds. Something. Yes, I know it sounds like they already knew from the start that one was that and the other one was that. And there's something which is called a Bell test, which proves that this is not the case. The recent Nobel Prize, I think it was. I don't know. I don't remember when Zeilinger got that. He was one of the first ones to actually prove it experimentally. That
this was in fact, this entanglement was in fact,
that it in fact exists. Einstein famously said that God doesn't play dice. This is exactly what he meant by that. He thought that there might be a hidden variable governing this, so something that we didn't know of, that the photons carried to actually switch at the end.
But we can't find one.
No. And the math explains it perfectly, and the experiment explains it perfectly, and it's all the way that it should be from our understanding of the universe. It's just not very intuitive. And that's what entanglement is.
I can't imagine, and you're working with this stuff, but I can't imagine going to work going, okay, this works. What? You know what I mean? Like,
yes.
Why?
You see the thing I do when I enter the building is I accept that this is the case.
Oh, okay.
And then I think about ways that I need to make sure to protect the state. So for instance, so as I said, observation is a crucial thing. So if there's strong magnetic field exposure, or in this case, there's some loopholes that you have to take into account. So information can't travel faster than the speed of light. And if you observe that one and then light has enough time to go to the other one, will the other measurement be affected of that and stuff like that? So these are very technical, very close to life, maybe for me, closer to life problems. Right? And my mind then works with these problems because I accepted that this little intuitive phenomena exists. And now I need to harness it, make sure that it works for me in the way that I want it to work for me.
But that's fascinating. So you're basically shifting your perception when you go into work to say, okay, this is my new reality. While in the lab, this is my reality. I may not perceive it outside, but that's fascinating. I mean, it makes sense. I think you'd have to, right? I mean, so my question, you mentioned the speed of light. When these entangled photons, when you look at one of them, is the change is it an instant change? Like, is faster than light? Really?
Yes, and it's not an information transfer. It's the collapse of the wave function. So you don't send any information. The one that doesn't send the information, I have been detected to the other one, and therefore the other one flips. But it's the entanglement. It collapses just into the state.
Wow.
Yes. This is why you also cannot transfer information with that. There's no possibility of transferring information. You can transfer some information if there's a prepare and measure protocol where you do the original, the source things a little different, and then the detection scheme is a little different. There are some options of doing that, but this is the original. So this is the actual entanglement protocol, and that works.
You could tell if something had been tampered with then, because if someone had looked at your communication, is this how they use? Is this what they mean by this? That's what they. Oh, is that it? Oh, okay. So that's
what they
secure
mean by
communication.
That's what they mean by the security of the quantum key distribution. So in principle, by that means
they've got to get better names. That's a terrible name.
Yeah.
We should name
it's
things.
QKD.
Yeah.
Yes.
Oh, QKD. That sounds better. That sounds better. I'll give you that. Okay,
yeah. So that's what I mean by having the two people at the two ends measuring the photons and the polarization. You can generate a key because there's some technicalities involved, but you basically agree on some things, and then you can generate a key that nobody else has but the two of you, because you two at your positions performed individual state measurements, and since you know. If one measures that, then I have to measure this. Then you have a key. You basically generate a sequence of zeros and ones, and then Alice can sort of take her general message, encrypt it with the key that you just generated, send it over, and Bob, because they generated the same key, can decipher the message.
It should really be Alice and the Mad Hatters who it should be, because that's how crazy this stuff is. You know what I mean?
Maybe the Mad Hatter's name was Bob.
Maybe it's Bob the Mad Hatter. There you go. Yeah, exactly. Bob the Hatter.
I'd like
there
to think Bob the Hatter. There we go. And you caught on that very, very quickly, and I commend you for that, because that is something that took me a while to understand. The property and this collapse is exactly how you know if somebody has tampered with it, and if somebody has caught the photon, one of the photons, and resent it.
They still would have read it, but you just would have known that.
You know it. And since you're only generating the key, you just start over. I mean, it's just photons. They come at the speed of light. You just start over. And as soon as
so we're all going to have these little photon splitting. Like, how do you do that?
Well, there are concepts for that, yes. So there are some companies right now that build something which is called a quantum random number generator, because in addition, here's the next trick with that. So in addition to the security that you gain by generating the key at 2 points, you also gain actual probability, at least for all we know. If there's a hidden variable, or if there's anything that we don't understand about it, or that we don't yet know about it, then it might be that the randomness that we see is not actually true.
Right.
But for all we know right now, this is a system that will generate true randomness. So all the keys that we're using nowadays to, I don't know, decrypt your WhatsApp messages, which is probably the worst example in history, because I don't think that they are encrypted at all. But say your bank account, your online banking, which is why they're worried about encrypted.
This is why they're worried about this post-quantum or whatever it's called.
Yes. So there's some level of encryption, but these encryptions are always generated by a computer. And there's a program behind it, which means you get finite randomness. So there's some algorithm behind it, and you can use other computers to study and understand the program which was written to generate the randomness, and thereby
basically recreate it and
kill the key, and then you can read the message.
But you couldn't do that with the quantum, because how would that be done then? How would you
exactly?
So generate a key with the quantum stuff?
So you, as I said, you have these entangled photons. You send them out, and then there's an additional trick with a polarization measurement on both ends.
Right.
And so you have to sort of turn a polarizator, a polarizing membrane at both ends. And when they are the same, you agree to take that measurement. That's just to introduce some randomness, but that's part of a bigger experiment. And that's what I meant before with some tricks.
Right.
And then by measuring the photons, the polarization of the photons, you generate the key. And then the two parties have the key. Nobody else has the key. And since the randomness was introduced at the point of the source, of the point of creating it,
of course,
there's no algorithm behind it. You cannot.
Yeah, it's completely. You have no idea whether it's going to be this way or that way until you look at it. There's no algorithm behind it that you could decipher and then understand the key and then decipher the messages. But you would have to actually purely by repetitive testing get the full key,
And as I said, it's a purely optical purely optical method. So measuring 1 or 2 photons more doesn't really take you that long of a time. Whereas actually testing for full randomness in 1 or 2 digits more can take months or years longer for a classical computer to decipher.
Yeah. Wow. That's amazing. So you get the speed as well as the security. Yes.
And the length. You get basically as long a key as you want them to have.
Because as you say, you just pop a few more photons through the thing, and wow,
it's fine.
Wow.
Yeah, if you have 100 digits or 1,000 digits or 10,000 digits, that's nothing. Wow. I mean, you just pop it into it, and you just measure 3 more times, and you're there. So this is the thing that people are worried about is quantum computing, which also works on entanglement. It's fun that you want to counter a threat that is brought on by the same effect. That, these are the things that make me chuckle.
You got a weird sense of humor, but okay, yeah.
That's news to you. Anyway, here we are.
We've spoken before. It's fine, yeah.
So the quantum computer should be able to calculate these algorithms much faster. There is something which is called a post-quantum cryptography, which promises to have classical algorithms which are written by a machine on a machine, and normal algorithms that are as hard to decipher for a quantum computer as they are for a classical computer. That's one way to go.
That's like the belt and suspenders. You got both. You do the old one and the new one together, right?
And the new one, yeah. And then in addition to that, you have the quantum key distribution. And that is more of it's more of a looming threat than actual reality at this moment in time. Quantum computers are still very much in a development phase. We've seen amazing rise in technology and achievements in technology, especially over, I want to say, the last 3 or 4 years. And I mean, you understand the geopolitical situation.
Apparently China's beginning is as we all are, I guess, is working on breaking these old codes using these quantum computers. So it just makes sense. It's like a quantum arms race.
Quantum arms race, yes.
You could be an evil quantum scientist.
Yeah. I mean, it turns out that in the movies, the evil scientists are usually evil engineers.
It's true. That's true. That is true. Yeah.
Maybe, quantum technology is so close to engineering.
But I just love the fact that we've got God playing dice to make the codes for us. I mean, that's what it's. I mean, it's such a complete difference from where I thought we were, where we were just talking about this weird stuff that may or may not, have an effect. How are you using this? So in at your institute, you are working on, I'm assuming, multiple different quantum related technologies. But what are the big ones for you right now? What are the ones that you're sort of most excited about?
So we spent quite some time now to talk about entanglement, and that's something that the institute in Ulm does. That's something that we are really not that interested in, and this is where I'm a little bit on shaky ground. I'm
glad we got that out of the way then. Good.
We got it out of the way.
Fine. Yeah.
I felt comfortable in what I said. There's probably some comments in the chat that tell me that I don't know anything, but here we are.
There's always that. That's why I'm here.
Always that.
That's why I'm here. Yeah.
What the phenomenon we are using most of the time is cold atoms. Right. So we are using, and this is again something that took me a while to get behind. If you're thinking about cooling and cold atoms and ultra cold atoms, and I love the way that this sounds. It's degenerate quantum gases.
Wow.
Yes, that describes a whole zoo of cold atoms and ultra cold atoms. And the thing that I initially thought when I heard that was that you would need huge cooling machines.
Yeah, that's what I thought, like giant fridge things. Yeah.
Yes. Some of the
away.
helium. Yeah, you would need helium to cool that, and then you do this, and then you get superfluidity and all these kind of things. And the fun thing is, and again, my sense of humor makes me want to do that.
You want the dry ice and the
dry ice
and the smoke and the fog
smoke.
and yeah.
Funny,
You're watching
funny
too many
enough,
movies.
Yes. Also, if like media companies come by and want to see stuff, they always want the fuming. So we usually have some.
You better have
liquid
something.
Nitrogen
Yeah, you need
somewhere.
a little liquid nitrogen just hanging on the side just to make it,
Yeah.
I should put some back
We just
here
have it
too.
Yeah, we just have it somewhere so that we can, put it onto the table and have it sort of whiff away and look cool.
Right.
But in fact, yes, you want to have the big entrance, right? You want to have the green lasers and then the whiff, and then you want to you know,
blinking lights, little blinking lights, lots of blinking lights. We love those. The Stargate was all blinking lights, It was like,
So what we use to cool the atoms is actually a combination of magnetic and optic fields. So we use a magnetic trap, which keeps the particles where we want them to be. It's very much like a cage, like as we said, the glass before. And
but the magnets are holding them down here.
Yes, we have so magnetic fields usually are not always mostly like a quadratic potential. This is why I have this motion. So you keep them in this magnetic trap, and then you shoot it with lasers. And I don't know, they get very they get very afraid, so they stand still or something. I don't know how that works, but
so they're firing lasers at trapped atoms.
Yeah.
Okay.
Yeah.
Wow. Okay.
That sounds more sadistic than it actually is.
Yeah, it does a bit.
Yeah, it does. So I guess
But that slows them down. So it's forcing them basically against this magnetic cup, so to speak.
Exactly. So that slows them down, and that puts them into the lowest point of the magnetic trap. And you use something which is called Doppler cooling. So you tune the frequency of the laser in a sense that the atom, in order to be able to absorb the laser, it needs to, sort of move towards it, which changes the frequency of the laser, which is the Doppler effect. You've probably heard that if an ambulance drives by. And
the same thing happens with the light. It gets redder, and you're right. Okay.
Exactly. The same happens with the light. And so we sort of slightly redshift it, and then when it moves towards the particle, it gets, from the perspective of the particle, blue shifted, and so it can absorb it. And this way, we can sort of stop the particle or transfer some of its forward motion, some of the kinetic energy, into the photon that it then emits in the end into some photonic energy, and that stops the particles.
Wow.
And so we do that from 3 dimensions, from 3 directions, which then is called a 3D magneto-optical trap, because we need the magnetic field and we need the optical field, and that is a magneto-optical trap.
Oh my God, but it's got to be so precise. I mean, the precision on that's got to be insane.
Yeah, well, yes. There are some very intelligent people working on it, and I'm happy that I don't have to adjust the lasers anymore.
I was going to say, so you're not 2 guys going like, a little to the left, a little to the right.
A little to the right.
Yeah.
No, that's
my eye. Yeah, it's not. No. Good.
Yes, yeah. There are stories to that as well. I've had my fun time in labs. I mean, now that I talk about it, I wanted to become an astronaut in between, and they scan your eyes, and they found a scar on my eye and said that that's probably a laser hitting my eye, and that's probably true.
Well, and that takes you out of the astronaut race?
It was the only thing that I could conceive from what they gave me that actually took me out. There might be some other reasons. My wicked sense of humor might have been up there in it.
You don't want to be a space hamster anyways. Come on. That's,
I would have loved to. Yeah. Just seeing the planet, Anyway, I digress.
Completely lost Lisa. Lisa has floated happily off into space.
I'm floating off into space. Oh, I would have really. I mean, I told them there is at this moment in time there is a machine that does that cools atoms, and produces what is called a Bose-Einstein condensate.
Right.
Currently on the ISS.
Oh, there's one on the ISS. Oh, really?
Yes, there is the NASA Cold Atom Laboratory, which is at this moment running on the ISS, producing these degenerate quantum gases, producing Bose-Einstein condensates from rubidium.
Someone's got to start a band called
using...
Degenerate Quantum Gases. They got to.
Yes.
Yeah.
Yeah. It's what you do.
But what are they doing with it up there then? What are they just seeing if it's different up in space or?
Oh no, there's a fun property of those. So if you cool them and put them into the trap, you can do fun things in the trap, but you never see an actual quantum phenomena sort of in the wild emerge from it, right? Because you still have the magnetic field interacting with them. And as I said in the beginning, anything that interacts with your quantum system
screws up your quantum stuff.
Screws up the quantum stuff. Yeah. This is not entirely true. There are you can do something which is called, oh God, I forgot. It's like called interferometry. So you can still use the wave-particle duality of the ensemble, even in the trap, even while it is interacting with the trap. That is still true. You can still do that. But ideally, you want the collatum system to freely evolve and to freely move, and you want to study freely moving and emerging systems from that.
So you smash you get all these things so close together and so slow moving that they stop any kind of vibration, basically, or most of the vibration that they would normally have.
Yes.
And then
there is still there's still a finite forward motion. So we are talking picokelvins, and picokelvin with the mass of an atom, which is very, very small, still translates to a rather large velocity.
Really?
So you can still, So if you let them free, if you open the trap out, they will still move. But there's, as you said, the important thing is they don't vibrate anymore. You cool what we call the internal states of freedom. So the external ones are motion. We cool those. But we also bring them into the ground state of the atom. So we cool also the internal degrees of freedom. That's they don't jiggle. They don't do any sort. There's no modes. They don't do anything of that sort anymore. They are very calm.
And what is the advantage of that?
So the big advantage, if you're taking bosons, and
we should describe what a boson is. What is a boson? Yeah.
So at the fundamental level, there's two types of particles. Humans have always tried to classify particles. There's all kinds of zoos, and one way to describe particles is based off of their spin.
Right.
The spin is a quantum property. It's a quantum number. Yes, exactly that.
I love that.
Exactly that. Yeah. The best explanation for spin I've ever heard is it describes the amounts of times that you have to turn a particle until it looks like itself again.
Well, that completely solves it for me.
Yes, no, that helps me actually. But anyway, so there are some things that you only need to turn half.
Right.
Like half. If you were to have a cube with no numbers on it,
right,
you would turn that half a rotation, and it would still look like itself.
Got it. Okay. Yeah.
Right.
Fair enough.
So that would have spin 1/2.
Okay.
It gets a bit more tricky if I tell you that I have to turn a particle twice until it looks like itself again. Then
there's
starts.
There's that non-intuitive thing again. Yeah. Okay.
There's that non-intuitive thing again. But I like it. I don't know if it's true. I like it. I'm going to use it.
Right. And it works. So Yeah.
So there's this quantum mechanical property which emerges if you're looking at atoms and how they behave in magnetic fields and stuff like that, which is called a spin. And the spin defines whether something is a boson or a fermion. And now, unfortunately, German has these words, and I failed to search if English has them.
Right.
But if the spin is it's uneven, right? 1, 3, 5, these are uneven numbers, right?
Yeah.
Or odd numbers.
Odd numbers.
These are odd numbers. Odd numbers.
Yeah.
So if it's any odd divided by 2, that's a fermion. So 1/2, 3/2, 5/2.
Oh, right. You've got special names for these things. Yeah. That's a fermion.
Yeah. That's a fermion.
Okay, right.
That's a fermion. And if it's got integer numbers, like 1, 2, 3, 4, 5, or 2/2, 4/2, 6/2.
I've clicked things.
Sorry,
I shouldn't have clicked. Hang on, sorry. There you go. Yeah, I was just checking to make sure that Agnes wasn't trying to get in touch with us because I realized that if I pull it up, it changes the video. Sorry. Go back. Sorry.
Of course. So if it has integer numbers like 2/2, 4/2, or 1, 2, 3, 4, 5,
right,
in spin, then it's a boson.
Right.
And these properties are additive. So if you're thinking about a proton and an electron, they both have spin 1/2.
Mm-hmm.
But if I produce a hydrogen atom, then I have two particles with spin 1/2. So it can have spin 0, or it can have spin 1 or -1, but it's definitely an integer number.
Right.
Which means that I put two fermions together, and that produces a boson.
Right. Okay.
And that works. That works. There is something which is called isotopes. So you can have one atom, and if you add a neutron to the core of that atom, then you still have the same number of electrons, and you still have the same number of protons, which is what defines basically its behavior in a magnetic field and an electric field and all these kind of things. So you still have sort of the same atom as such, but it has one proton more, so one neutron more, so it's heavier.
Right. So still the same thing, only different.
Only different.
Right.
And that is an isotope.
Right. Okay.
So if you look at the periodic table, what you probably have seen is like a rectangular thing, and the one I'm used to is sort of really spread out because it has all the isotopes. And some of these isotopes, you might have heard, like there's carbon 14 and carbon. Yeah, so these are isotopes of carbon which have different so-called half-lives, which already tells you that some of these isotopes are not stable.
Right, right.
They will just decay, like uranium 239, 238, I don't really know. So that's the number that it has.
Yeah.
It's sort of the
and it's not stable, so because of that.
That's not stable, and it will decay. We can go into all of that, but it will decay, and so some of them are unstable, some of them are stable, but you've heard about isotopes usually.
Yes. Yeah.
They usually come up at some point.
And the things that we create, like in the collider and stuff, those are all particles that form and disappear very quickly because they just don't. They're so unstable, right? Right. Okay. Got it.
They are super unstable. Yes.
Right.
Now I get to be a bit of a patriot.
Very good. Okay. Yeah. Please.
There is a big collider which is close to my hometown, which is called the GSI, the Society for Heavy Ion Research.
Wow, okay.
And they were able to, I think, so the latest one are American, but there was a time when this... America! Fuck, yeah. Sorry.
Someone's been watching Team America.
No, I would never say anything on the television which might be controversial in any way. Anyway, so there are... and in between there was this German facility which was able to generate a lot of these isotopes of these elements, and so they are called Hessium for the state that it's in, from the state of Hessen, Darmstadtium from the city where I was born.
Darmstadtium.
Darmstadtium. I'm born in Darmstadt. There's Darmstadtium. We even named a building after it. It's very important.
Really? There's a Darmstadtium building?
There's a Darmstadtium building.
They should have a Darmstadtium stadium.
Yes, no, we have a building. We have Merck, which is also in Darmstadt. We have the Merck Stadium. So
very nice.
There's more money in chemicals than there is in particle physics, but
for now,
here we are.
For now,
for now.
Yeah.
And so there are a couple of these that, looking at the periodic table, I can identify as coming from my hometown.
Wow, that is very cool.
However, so you can produce those as fermions and bosons, as I said, simply by adding a neutron. The neutron has been 1/2, and so by that you can basically produce whichever thing you want.
Right.
And so since this is an additive function, we can look at atoms that are bosons and atoms that are fermions. And from here on in, I'm going to focus on bosons.
Okay.
You can do similar things with fermions. The mechanics is a little different, but
we'll go with the boson because they're nice even numbers.
They're nice even numbers.
Right.
Maybe I have to diverge from that statement a little bit and talk a little bit about fermions and then go to the bosons. So the fermions, they, for some reason, which I have to admit, this is part of what I said before. I accept that it is this way.
Right.
And then I'll work around it.
You don't have to like it, but you'll accept it.
I don't have to like it.
Right.
I try to understand it. I always came to a point where they said, the math does that. And I'm like, perfect. Mathematics is great, but I would like to intuitively understand. And they're like, no, it's that way. And I'm like, okay, perfect. It's the -1 in the denominator.
It's not the same.
They're like, yes. Yeah, that's that. And I'm like, yes, perfect. That's that. I don't. Anyway. So if you're thinking about fermions, they have to obey what is called the Pauli principle. The Pauli principle says that two particles, two fermions, cannot be in the same state.
Right.
And that is the analogy that I find sticks most with people, is to look at public transport. So if you're looking into a bus
analogy.
or a train, people will usually try to sit on an individual chair, preferably not next to one another.
Yeah. Yeah.
This is a fermion. You stay on your chair.
I'm a fermion.
Your chair is good.
Yeah.
Right? And you fill up the entire bus.
Right.
Evenly, preferably.
Right.
So you sit on your chair. This is fermions. Bosons, on the other hand, bosons, they don't have to obey the Pauli principle. And so they don't. And the best analogy to think about that is if you're thinking about teens in puberty, they will all sit at the very end of the bus.
Yeah.
And for some weird reason, they manage to sit in the same chair.
Yeah. Yeah.
You don't know how that works.
Just a pile of them at the back.
It's a pile.
Yeah.
There's piles of.
Got it.
They are all cool guys. Right?
Bosons are the cool teenagers of the quantum
I
world.
wanted to be there. Yeah, all my life I wanted to be there, but turns out I like to obey rules, so I'm a fermion. It's a bit of a shame. But so this is why we love bosons.
Right.
Because if we're now thinking back,
because they're grown-ups. Because they act like grown-ups. That's why.
Well, yeah. If you're thinking back to our magneto-optical trap, you have the magnetic field and the optical field.
Right.
And if you now put bosons into that, they all want to be at the bottom of that. They all want to be clumped together.
Yeah.
They want to be cool, so you can cool them. You get all of them into the ground state. You get all of them onto the same seat, which is the ground state, right? So you get them all into the ground state. You cool them, and then at some point they do a phase transition, which is also what teens do. Then suddenly there's this clump of them. And this is exactly what happens here. We have a phase transition. So phases are usually something that you will know, like gas phase and water, like liquid phase and
they went and added
solid
plasma.
phase.
Yeah. Yep.
And the plasma. So there's these usual phases, and then you can have, if you're cooling and cooling and cooling, you get another phase transition into a Bose-Einstein condensate. And that's an amazing state, because now we know that they are all in the same state. And their wave functions sort of melt together so that you have one overarching wave function and no longer individual wave function for all of them.
Oh.
Exactly what happens to cool teens in the back of the bus. They are just one thing.
Right.
And no longer individuals.
So you've turned the bosons into teenagers, basically? Is that the...
Yeah.
To some extent?
Maybe,
I mean,
yes.
they're now clumping
cool
together in a
teenagers.
way that they don't want to do.
Oh, they do want to do that. They want to do that. They want to stay there, and we clump them together, and then they are just one pile of happy, cool guys.
Oh, that's the fermions, though, not the bosons.
No, that's the bosons. The bosons are the ones that we can cool to the ground state. The fermions will have to obey the laws and sit in the individual seats on the bus, and we can't put them all into the ground state.
Okay. All right. Got it. All
right? And then the teenagers are the ones that clump together in the back, and that's the bosons.
Okay, I got the mixed up again. I tend to do the switching thing. Yeah.
No worries. If you get it wrong, that means I'm explaining it poorly, which means that other people don't get it. So I'm happy for you to ask again.
That's very kind of you.
No, that's a reality.
Yeah. Wow. Okay. So we've taken advantage of the fact that they like to clump together. We've shoved them all into this thing together. This stops them all having their own separate little quantum wave things going on, and they all become one, like, freezing mass. Yeah.
Yeah. Exactly. They're still gaseous, funny enough, but yes, these are cool, very, very, very cold, degenerate quantum gas.
Right.
So it's a real ensemble. They have a phase transition, and now we have a fun thing, because you asked me what the advantage of space is.
Yeah.
Now we have this very, very cold ensemble of bosons, but they still have to obey accelerations. They still have mass. So, for instance, if the bus breaks very fast, they have to all fall to the front, right?
Right.
The same happens here. So if I open the trap, even though they are all super, super cool, they will have to fall down following the laws of gravity. And if I put them to the ISS, and I'm going to make that point because I sort of have the opportunity now, is not weightless. The ISS just happens to miss the ground very elegantly, to quote Douglas Adams. They just miss the ground continuously. They fall in the gravitational potential of the Earth. So
it's going like 180 kilometers an hour or something.
They fall very fast, and they fall very elegantly, and they do it quite nicely.
Right, yeah.
But so they fall with the particles that we now let out of the trap. And so everything falls together, which means that it appears weightless to us. We can do things with it, and we can see them for a prolonged series of time. So there's...
And you have that extended time because you're out there in space. You've got that. Yeah, okay, got it.
Yeah, and we still... So our chambers... I should have probably brought it here, but, well, our chambers have an inner diameter of around 10 centimeters.
That's it?
So, that's it.
It's hard to show that off when they come visiting, isn't it? Like, it's just like it's my little tube. That's it. Yeah.
That's it.
Yeah.
That's it.
But but how long are these things? What?
About 6 centimeters.
That's it. That's the length of it? I was thinking that's how wide it is.
Yes. Nope.
Really?
No.
Okay.
It's around 10 centimeters. In all directions.
But you'll get a prolonged period of them falling in that chamber.
The thing is that since the chamber falls with them, so I don't think that translates to the screen, but if you want to do that, what you can try is if you have a big keychain with multiple keys on them, what you can do is you can throw that in the air. And what you will see is that the keys, even though they are connected, that's not the point, but that they will also sort of stay in the same vicinity. Whereas they will build like this clump which sort of extends in different ways. Whereas if you hang it, and that I can show maybe.
Right,
like
they all stick together.
This is what that's what they look like. And if I throw it, you will have more of a ball.
Right. That makes total sense. Yeah.
And so the same happens here. Since the chamber falls with the particles, the particles don't fall out of what I would like to call the active area.
They do
but
their
they
nice
stay.
Okay.
They stay there. Of course, as I said before, they still have some forward velocity, so the cloud will expand and we will lose them because they just hit the walls in all directions. But they will fall with the chamber, and so they won't move away from the chamber. This is why you want to go to space, because then you can remove the trap, you can observe them and manipulate them, and as you can do with teens as well, but you can insert some...
They manipulate us. I don't think that's,
Yes. In this case, we manipulate them by introducing some different lights. There's some fundamental research on forming bubbles and surfaces and looking into surface interactions with the magnet. So there's something which is called an atom chip in there, which has a magnetic field and some surface layers, and you want to sort of investigate surface interactions with that, and there's all kinds of fundamental physics that you can do.
And you can observe that because you've bought yourself extra time by them falling in space as opposed to falling on Earth.
Because the chamber falls with them.
Yeah. Okay.
So they stay nicely, sort of where they are in comparison to the chamber.
And
whereas on Earth.
Sorry, yeah. Finish. Whereas on Earth,
they just fall.
Right. Yeah. So, and how are you observing this stuff then? How are you seeing when you say you're examining them? How are you examining them? How are you testing to see what? Because doesn't that mess with everything when you start looking at them again? Isn't that the?
Yeah. Yes. Some of these things do. So there are different kinds of experiments that you want to perform. But in the end, you want to see what you did.
Right.
And to see what you did, you usually just shine light on them, and they will absorb the light and emit it again. And then you have a photodetector on the side and observe the pattern that you see in the wavelengths that they emit. And then you can learn something about it. There's some, especially for the bubbles, you would make timed sequences and stuff like that.
When you say bubble, what are you bubbling? What is the?
So the BEC itself is a homogeneous thing to start with, and then you can build sort of voids in the center of that and build bubbles of these particles. And,
oh wow!
And have them generate. Yeah, that's some experiments that especially the American colleagues are performing on Cal right now.
Wow.
We are most interested in what is known as atom interferometry.
We're getting into your satellite stuff now, aren't we?
Yeah.
Yeah.
Yeah. So atom interferometry, as I said, we have this overarching wave function.
Right.
And if you have something that has this property, people have also called it a space atom laser.
Ooh, I like that. That's good.
Yes.
See?
It sounds fancy,
I'm not
doesn't
allowed to
it?
name things, but I like that. Okay. Yeah.
Yes.
Yeah.
And that comes from the coherence of the state and the waves that you can describe it with. And with a laser, you would perform interferometry.
Right.
For instance, to measure vibration. So you can use something which is called a Massinder interferometer, where you start off with a laser beam.
Mm-hmm.
You have a beam splitter, so you split the beam in two.
Right. You love those things.
Then you need two mirrors,
Yep.
bring it back. And now comes a bit of the tricky part. We're going to look at that one first. You have a beam splitter, so you split this one into a beam that goes straight through and one that diverges. And then for the other one, you do the same. One that goes straight through and one that diverges. And so you get two readout ports where the two arms that you have created basically overlap again.
Right. Right.
And for these optical Massinders, you could either introduce some material that one of the arms goes through, which introduces a phase shift, which could then be seen in the interferometry, or you introduce the mirror to something where it vibrates or where it shifts away to measure how strong the vibration is. For instance, in an earthquake, you could do that, or
Right.
Where you want to have a relative measurement to what it was before.
Right. Right.
And now we're going to turn all of that on its head. So that which was matter before now is lasers, and that what was lasers before is now matter.
Ha.
Yeah,
Wow,
I know.
Yeah.
Please, you have to stop me if you're not following it, or if you feel like I should repeat something.
No,
because I will keep talking.
That's good. No, I'm loving it. Are you kidding? I'm loving it. So explain the matter light. The light is matter and matter is light again. Why do you say that?
So we started in my example right now. We started off with a laser.
Yep. It's
But I
bouncing off
went
the
to
mirrors.
great lengths and the mirrors, and I went to great lengths to explain to you that my cool dudes, my bosons, now behave as a laser. So instead of a laser beam, I use the bosons.
Oh, okay.
And instead of having a glass cube for the beam splitter, I now use a laser to act as a beam splitter.
Ah, okay. Wow.
Because quantum mechanics is so governed by probability. By shooting a laser beam through the Bose-Einstein condensate, you will have half of them absorb the photon and sort of be accelerated upwards, and half of them will simply ignore that.
Right.
As
Just keep
teenagers sometimes do.
Yeah.
They just stay where they are.
Wow.
And so you have created a beam splitter, right?
Right.
You have separated the two.
But done it with a laser.
You've done it with a laser.
Yeah. Okay. Yeah.
Now, to interfere them, you want to bring that one back up.
Mm-hmm.
So you need a mirror.
Right.
Right? The upper one's ignoring it, and the other one's coming up.
Mm-hmm.
And now we need the last beam splitter to generate the two output ports, as before. So we're doing the same thing. We generate the two output ports. It's a bit of a simplified image, I know. But you generate the two output ports.
Using a laser again to do that?
You're using a laser again to do that.
Right.
So you use 3 laser pulses, beam splitter, mirror, beam splitter.
And each time you're always going to get that 50-50 thing, every time you do that.
Yes.
Wow.
Basically, yes.
Okay.
There's some tricks you can do, but basically, yes.
Yeah, okay.
And you're, of course, only looking, so what you get in the end is this kind of rectangle. I think it's a prism.
Yeah.
Anyway, this shape. And so you're ignoring all the other paths because you really only want to look at that where you recombine.
Oh, I see. So if they don't do what they're supposed to, you can sort of cut that out of your
Yeah, you just ignore that.
Okay, great.
Yeah. So that's the ones that you are interested in. And you have the readout ports.
Okay.
And in the readout ports, you even get this interferometry signal. So you get stripes.
Right.
Or basically a state population in the end, and that you measure by taking a picture of it.
So you're literally seeing a pattern of what these little boson fellas are doing.
Yeah.
Wow.
Yes.
Now why? Yeah. Okay. Now the next question is why? How does this help you? What are you going to use this for now?
Yes. So the fun thing is that now I have not, as I said before, even in the Massiner, in the optical one, what you want to have is to introduce a phase shift,
Mm-hmm.
because otherwise, this is fun to do
Mm-hmm.
from a fundamental perspective. This is very interesting to perform these experiments, but what you want to do is introduce some sort of a phase shift.
Right.
And the phase shift one thing to do is to see if everything falls at the same rate. So in this case, the phase shift is introduced by the gravitational field that these particles are still subjected to. Remember, we are just falling around the Earth.
Yeah. We
leave them.
Okay.
We leave them out.
Yeah.
But they are still falling in Earth's gravitational field.
Right.
So we still measure. We still fall.
Mm.
And Einstein postulated.
Mm.
I mean, if we would have more Einstein's, life would be great. But Einstein postulated that everything would be falling at the same rate.
Right. That's the feather and the bowling ball and the whole. Yeah. Yeah.
Exactly. Again, this is very unintuitive because that does not seem to be the case in our lives.
Yeah.
But that's because we have an atmosphere. We have air. This is why a feather falls so much slower than a bowling ball.
Right.
There's a fun video on YouTube from, I think it's Apollo 11.
Yeah, where
they drop a feather.
Yeah, and what was the other thing? It was that, and I can't remember what else they dropped. It was
a hammer, I think.
Was it a hammer? But I love they're like, oh, good, okay. They're like, they landed at the same time. Whew, okay, good. We got here safe. We'll get home okay. Yeah.
Good. Okay, let's move. So actually, there's something that we do or we did when I was still with Max Planck, which was a day of the open door, where you would have the general public come in, and we would always have a tube, which where we pumped the atmosphere out and where we would have a feather in, and then you could see that the feather actually falls at the same rate as the ball outside. So just, some hands-on experience as to what that is.
Right.
And now you could use this interferometer because it's super sensitive to relative distortions.
Right.
So not to
Any
absolute
changes. Yeah.
Any change it sees in the acceleration, because remember, these particles still fall in the gravitational field. They still have mass, so they will still fall. This will introduce a phase shift in the readout channel. So the trick now is to find two bosons with different masses to do that. And for our experiment, so Cal is currently in orbit, and I think they are introducing potassium. But definitely we are building something which is called BCAL, the Bose-Einstein condensate, called Atom Lab, which is going to go up to the ISS, I hope, in 3 years' time.
Sweet.
And we will have, I'm so looking forward to the day when we put it onto the rocket and we stand on the launch pad and see it.
Oh, I can't wait. Yeah, it's amazing.
It's amazing. It's a lot of hard work.
Yeah.
And I hope that, I can't wait. And so that one will definitely
your teenagers off. Your teenagers are leaving the house.
Yeah, you see your teenager off, you wave.
Bye, don't come back.
Happy bye, don't come back. Bye.
Yeah.
Enjoy.
Have a nice fall. Yeah.
Have a nice fall, exactly.
Yeah.
And so we will have potassium and rubidium on board.
Right.
The difference between the two is not huge, but they have different mass.
Right.
And the interferometry should be sensitive enough to see if there is a difference between the two falling in the gravitational field.
Wow, okay.
We expect something which is called a zero measurement. So we expect that there is no difference.
Right.
But, there is still the test. There's even a European mission which is called ST Quest, which builds a bigger chamber, or foresees a bigger chamber on a satellite to do just that, to perform this kind of experiment. It's not funded at this moment in time, which is the sad truth, but that's
it always comes down to funding, doesn't it? Yeah.
Yes. Money makes the world go round.
Yeah.
And the quantum's cold.
And the quantum's
it's what
cold.
it is. It's what it is.
Money makes the quantum's cold. I like that. That's a T-shirt. You should sell that at the institute.
Yes.
Okay, so you've got these things. You're able to see very, very tiny differences, and if they're there, and so you're double checking to make sure we've got this whole gravity thing down properly. Right.
There is another thing to that. So this is the so-called weak equivalence principle, that everything falls at the same rate, and the other one is if you're looking at Newton's law. The form of Newton's law you might know is force equals mass times acceleration.
Right.
Actually, it's a bit more complicated than that if you're looking into gravitation. It's force equals a gravitational constant times your mass in the Earth. If we're talking about you and Earth, your mass, the mass of Earth, divided by r squared. So divided by the distance between you and Earth's core, I have to say, squared.
Wow, okay.
Since this r squared is basically constant for all of us, and we hope that what we call big G, so the gravitational constants, is the same for all of us. Big G divided by the small r gives this 9.81 meters per second squared.
Right.
And you might have heard that if you take one of these boilers, these water boilers, to a mountain, that the gravitational impact there. No, is that right? Anyway, so the idea is that the gravitational force is less if you go to a higher place. So if you go to a mountain, then you will have a lower acceleration towards Earth core because the distance gets larger. So you divide by a larger number, and thereby the number gets smaller.
So the space station is a nice large number for you to be dealing with. Ideally.
Yes, the space station is a nice large number. Yeah. But the big question is do we have big G? Do we have the gravitational constant then? And that is another experiment that is performed both on Earth and to be performed in space to really measure, because we know the distance on the space station, it's very constant, and and we know the mass very, very well, to really measure the gravitational constant and bring that back down to Earth and have that be part of all of the things from GNSS to waiting.
GNSS, so what we would call the GPS. Yeah, right. So basically, you're getting more and more precise a measurement for this constant, which allows you to be more and more precise in however we use these technologies and such.
Yeah.
Wow.
Yeah.
And then, and is that when people talk about, and you talk about quantum communications, is that part of it? Is the communicating that information, or is there, because there's also actual communications as well, is there not, that you're using this stuff for? Or?
Yes. So the quantum communication and the cold atoms have some overlap.
Right.
But that overlap is very specific and a little tricky. So there's something.
They're kind of two different things then, basically.
They are kind of two different things.
Okay. Right.
You can use the one to aid the other and the other to aid the one. So there's also some things where so you always have some noise. And there's some ideas of using squeezed states, it's called, which is basically entangled state, to reduce the noise in the system. But that's all a bit far away.
Okay. Let's take a break for 1 second. I'm going to bring up the chat so we can see what Agnes being saying, if she's saying anything. I'm not sure. She was going to get some questions for us, and maybe we can go back and check in with people. There's a few little hellos I should say, because GPG Gaming is here. Fantastic. Has a question for us. This is my friend Lance, who's always got interesting things to say. He says Sabine Hoffenfelder is saying quantum computers are not useful and will stop being made. Is she full of beans? We don't know what she's eating. We can't speak to that, but yeah.
No. So quantum computers, I think there's a huge hype around quantum computers. And my personal opinion is that hype is unfounded. However, that being said, there were people who said back in the day that the personal computer would not be a reality, and I guess all of us.
I said that. I was like, no way, we're not all going to have computers at home. Good luck. Yeah.
Nobody, ever. And I think all of us right now, all of you guys watching, you, me, Agne, every one of us, is sitting in front of a personal computer. We are not sitting in some big center using a big machine.
I know. I'm not logged into my local, mainframe. Yeah.
So this might be wrong. However, the thing that might be right is that quantum computers, or the danger with quantum computers, is they are not going to be superior in everything. There might be something in the end which is a personal quantum computer, PQC.
Oh, I like that.
Yeah. So that might happen in the future. I don't want to fully rule it out. Technology is advancing really quickly in the field, and there are some systems that can produce entanglement without cooling and without large cooling systems. So that's absolutely a reality. But they might not be superior in every aspect. They are superior, or at least from what I'm understanding, they are superior in ideas that we had covered in the beginning, where you want to say where we want to decrypt algorithms. This is a purely mathematical challenge. This is just, repeating it over and over again and see until you come to the end. This is something where I think that quantum computers can actually excel at. So the big threat that is seen is probably true.
Right. So it's more specific tasks, you think, rather than general computing that's going to be influenced by this?
Where they are going to be better. You might be able to use them for general things, but they are going to be better in very specific areas.
Right.
And that's an important, from my point of view, that's an important discussion to be had and an important idea to be set. There's something, I forgot the name, non-solvable problems. They are different. So there are problems that we put to a computer and they will simply never come to the solution for it.
Right.
And some of these problems could be solved using a quantum computer simply because a proper quantum computer could be very, very fast.
Wow. Again, in theory at this point, not actually in practice. We haven't quite figured that out. We've got a number of qubits now together, but not as many as we need.
We've got a few, and it's not a bad number. And the thing is that a normal computer, if you're not thinking about normal bits, you have one bit, and that's 1 or 0, and then you've got another bit that is 1 or 0, and so one bit more just gives you one operation more.
Right.
And a qubit, we had that before, this is the entangled state. It's going to be 1 and 0 at the same time. And then you're going to entangle that to the bit next to it, and so they are both now in a system where they can both be 1, both be 0, and both be 0 at the same time.
Right.
And they have this 50% probability. That means that you don't, if n is the number of qubits, you have 2 to the power of n number of operations that you gain, as opposed to with the other one just linear n.
Right.
Right. And so if we're getting just 1 more, we get a factor of 2 more than what it was before, and there is
You're jumping ahead with.
You're jumping ahead, and if you want to think about that, there's I think it's like a historic tale, cautionous tale of the chessboard.
Right.
Where they said, if I beat you in chess, I double the rice corns.
I get like a grain of rice for every whatever yeah.
And then I double it for each point, for each field. And
Right.
2 to the power 64 is quite a huge number.
Right.
And that is what would happen. So with normal bits, you would have n, so 64, and with quantum bits, you have 2 to the power 64.
Wow.
So to get to a reasonable number, because of this entanglement, right? Because of this simultaneous state, if you get to a reasonable number of entangled qubits, and that's still a big challenge, you get to an immense computing power. And I think I've seen something, they claim 500 or something, that's IBM, but people have told me that they don't really think that they are all entangled, so you can't really count it that way, and it's a bit tricky. Keeping the coherence between all of the different qubits is difficult and stuff like that.
Well, yeah, because they're dealing with like a tiny chip, and the rest of that huge thing is all just cooling.
Exactly.
Yeah.
That's what I said before. In this moment, it's not important to think about how entanglement works, just to think about how it breaks.
Right.
And temperature is temperature gradient temperature is one of the worst things you can do, so you want to cool it.
And these things are so sensitive to everything, right?
Yes. So you need huge machines to keep them very nicely chilled, and stuff like that. So there's, I think NV center, so that's a very specific center where if you take a diamond and you take out one of the carbon atoms and replace it with a nitrogen, the nitrogen has, I think, fewer electrons than the carbon has, so that creates a hole. That is what is called a nitrogen vacancy center in diamond, NV in diamond. And these are systems that potentially don't need to be cooled, but they still act as quantum systems, and they have, NV centers, for all it's worth, are amazing. You can throw them at any problem. You can create computers. You can create entangled sources. You can create magnetometers. You can create a whole zoo of stuff with them.
Just by pulling out that atom of...
Yeah.
Wow.
And replacing it. I'm going to insult some people now. They are not doing the best job. There are other quantum systems that are doing a better job, but NV centers are going to always do a fine job.
Right.
They're
more stable than...
Yeah, they're just easy to handle, or relatively easy to handle. They are a solid state system, and you can, have them sit there and you pull a laser in and you get some signals out. And so they are going to do a decent job, but not the best job in the world. However, they might be a good candidate if you want to build a high number quantum computer with a high number of entangled bits, because you have this diamond where you have these NV centers in, and you don't really need to worry that much of cooling in that, because the diamond doesn't move anyway, or very little. So there's some advantages to that.
Right.
This is not the full solution, and I don't know enough about quantum computing to sit here with full confidence and say if you build it based on NV centers, life's going to be good.
But
I'm just going to say that
they're not to be dismissed.
Discarded.
Right.
Yeah.
Right.
So they might be, if you wanted to have a personal quantum computer, I would put money on that the first personal quantum computer is based off of NV centers.
Really? Okay.
Simply because they are easy to handle.
Right.
Or relatively easy to handle. You still have to do stuff, right? You still have to take care of them, but they are relatively easy to handle.
Right. Just got to get a bunch of diamonds. How hard's that?
How's that?
Yeah, diamonds and lasers. Just punch a few holes in them. What the heck?
Lasers,
Why not?
what the heck?
I got something kicking around here. I'm sure I got a diamond or two. All right,
it's not that difficult. I don't understand. So to come back to the question, I don't think they are completely a waste of time. I just think they are slightly overhyped.
Right. Okay. I feel like that's always the case, though. Like, it's like the crypto bros get all excited about this whole blockchain thing. Cool technology. Let's find out how we can, rip lots of people off with it. I feel like the same thing's happening with AI now, too. Everyone's freaking out about AI, and I think probably over expecting a lot of stuff. The quantum thing, I could totally see that. I guess you need to, like we've said, it all comes down to funding. So the more excited you can get people about this stuff, the more money they're going to throw at you. So, let's get excited. Yeah. Exactly.
And if I get money to fund something that is an NV center, and then I just understand NV centers very well, and in the end I'm able to, if the funding declines, I'm able to build a very good magnetometer, then I have learned a lot for another area, another sensing area, or for quantum communication or something. But I've still educated people on this thing. I've also grown the economy. I've generated a net worth. I've generated something that people can benefit from. I've educated people. I've built this new magnetometer. I understand how these things work. I can foster technology, all of these things. But yeah, the thing I'm most worried about, because I'm very much on the sensing side. I enjoy quantum sensing for acceleration.
Oh my God, it's brilliant. Like, I mean, how do you get more sensitive than at the quantum level? It's fantastic.
Yes, you get super sensitive. So I have I have a slide which says it's not a bug, it's a feature, simply because that is true. So in the days of quantum mechanics, which are still, right, there's a lot of laboratories, you would have these huge laboratories where these experiments would fill whole rooms, and you have this one postdoc which can operate it if, I don't know, the full moon is in Libra or something.
Right.
And so it's magnetically shielded and sealed and whatnot. But that tells me that these things are super sensitive, which gives me a fantastic leeway to sense all kinds of things in the world. Anything I want to. Another colleague of mine said, we have solutions, give me our problems. And that's very true. So I talk about challenges in quantum technologies, but if you have a problem because you want to sense something, but you can't, then a quantum system might help you, not so much with human emotions. That's more the AI part. But here we are.
Yeah. That's a classic bug as a feature, because it's the first time that I've heard it, it actually is legitimate. These things it's so easy to knock these things out of. Wow, perfect. Let's use that to measure things. Yeah. So what do you measure with them? What kind of stuff are you measuring with this stuff?
So a big thing is magnetometry. magnetic fields.
Yeah.
I've seen so many amazing things with that. That's not with the cold atoms. You can do that with cold atoms too, but they are way too complicated for that. You do that with the NV centers and some other systems, so-called Rydberg atoms, fun things. But you can measure heart flows, and you can measure muscle, so magnetic signals in the muscles to make them
Really?
contract electromagnetic signals. Yes, and there are people who were able to measure that, and also brain, right? The brain also has a lot of electric and magnetic signals that it excretes, or basically a current that is running from A to B always creates a magnetic field. That's very basic physics, usually taught in school.
And this stuff would affect
insulting anybody.
Would affect your bosons in a way that you could then register as some kind of data of some sort.
In this case, you don't really worry whether it's bosons or fermions because you don't cool them.
Okay.
But what it would affect, there's something which is called a Z-man effect, and that so.
Z-man effect. Okay.
Going a little bit back, there's something which is called the Schrödinger's equation.
Z.
Yeah. Yeah. Yeah, Z-man rolls nicely. So rolling it back a bit, if you take the Schrödinger's equation and you apply that to an atom, you get something that are called energy levels. And these energy levels are discrete.
Right.
Which means
that's the quantum, right? That's the quantum of. Isn't that
that's
the
quantum.
Yeah.
So I'm going to use the cupboard behind you again. I hope cupboard is the right, way to describe it.
IKEA.
IKEA.
Yeah.
So you can put you basically have these levels as well, and you can put a book in one level, and you can put a book in the level below, but you can't put it in between.
Yeah.
And that's exactly how atoms work. You have these energy levels, and they just stack, and you can put electrons on each of these levels. Again, they want to behave like the people in the bus. They want to sit on their own energy level.
Yeah.
And so they sit there, and you can put them on different levels, and
but not between
these energy levels are, but not between them. And if you excite them, then what's going to happen is what is called a quantum leap. So the electron is going to jump from one energy level to the next. It's very small. Quantum leaps are the smallest unit that you can do. So if you're going back to your cupboard, if you take a book from one shelf and you put it one shelf above, that's a quantum leap, because there's no possibility of putting it anywhere in between. It's the smallest step that you can move the book and let it go again.
And is that when it releases energy, when it jumps up or goes down? I can't remember.
When it jumps down.
When it jumps down.
When it jumps down.
I see. It releases energy.
So Okay, got it. It's the same with a book. If you move it up, you have to work against gravity.
Yeah.
So you have to put in energy. In principle, if you move it down,
if you're
really energy should be released.
Yeah. Right.
We still have to work our muscles, so things don't work that way in this example.
But you get the sense of it.
That's basically the idea.
Yeah,
that's basically the idea. Now, the Zeeman effect tells us that some of these atomic levels, some specific atoms, split these levels if they see a magnetic field, which means you introduce additional levels.
Okay.
And the energy distance of these levels is linearly dependent on the magnetic field. And that means if
you're adding shelves between the shelves?
That shelves between the shelves.
Okay.
You basically introduce shelves between the shelves. Also, you remove the original shelf, but that's a different idea. So shelves between the shelves. And you can now sort of probe that, right? You send in a photon that covers this distance, and by tuning the wavelength of the photon, you will know how big of a magnetic field the system sees, because at some point you will have the quantum leap.
Right.
And it's quantized. So there's only at this one frequency, only at this one energy, only if you put this very, very specific energy in, it will do the jump.
Right.
And otherwise it doesn't. So it sits, you put in the laser light, it sits, nothing happens, and suddenly you hit the right frequency, not the right intensity.
Oh, it's not intensity?
It's not intensity. This is what Einstein got his Nobel Prize for. For the photoelectric effect, intensity doesn't matter. there's something which is called a two-photon process. But in principle, intensity is not what matters. It is the energy per photon. It is the wavelength.
Really?
So you tune the wavelength.
That makes sense in a way. I mean.
Yeah, it does. If you think about it, it's not just. Again, first we would say, more intensity, more energy.
Yeah.
Great. Yeah, no.
Hit it harder.
Unfortunately, that's not. Hit it harder. No. You have to change. You have to change frequency.
Wow.
And then the photon has a different energy, and because only one photon is absorbed, it's only that energy that counts. To a certain extent. You can also do something which is called a two-photon process, where you absorb two photons. That's then just intensity because you have more. But we'll leave that out. I'm just confusing people.
Certainly me.
That's
yeah.
We're leaving that out. So
I'm still marveling over the fact
counts.
that we have these different levels, and we're adding. Yeah. We're rearranging all the shelves.
We're adding shelves.
Yeah.
But look at your shelf.
My
behind you, there are also
time.
shelves.
I rearrange it all the time. That's true. Yeah.
On the other side, you have shelves and shelves.
Oh, I do. Oh my God. I'm a quantum physicist. I didn't even know it.
You're a quantum. I told you.
There you go.
I told you. It's fine.
I'm like a quantum interior designer. That's what I do.
There you are.
Yeah.
There you are.
Right.
Yeah. And so by this specific wavelength, by knowing the specific wavelength at which the electrons sort of jump, we will then be able to know about the magnetic field that they are in. And since these jumps are small and the wavelength can be tuned very carefully, we will very well know about the magnetic field. So magnetic field sensing is definitely something that is going on that people are super interested in. And now there is one thing where I'm extremely jealous, and I don't mind them knowing. There is a university in Austria, and they built a quantum magnetometer based on, I think it's rubidium. So they have just a warm vapor cell of rubidium. It's not fancy, it's just a glass cell. It's fancy enough, right? Don't get me wrong, it's difficult enough. And this glass cell is currently flying on the JUICE mission, the ESA JUICE mission, to Jupiter.
Going to Jupiter. Or the moons
going
of
Jupiter.
to Jupiter.
Yeah, I think it's the moons of Jupiter. Somebody told me that there is a lot of bad Greek mythology in it, because you send Zeus, and then the name is like the wife of Jupiter or something. I don't.
Oh, really? Okay, all right.
I completely lost it. I don't know, but there's
not
some,
science.
There's some things. Greek mythology.
Yeah, it's just the naming again. It's all this naming. Naming's always the problem. Yeah.
Naming is always the problem,
yeah.
And money. And so they have the very first quantum magnetometer on its way to a really deep space mission.
Right.
To go to Jupiter and investigate the magnetic fields of the Earth, of these planets, of the moons, and you learn so much from the magnetic field alone. And that is super interesting.
Because you're literally able to figure out what it's made. Like you can figure out what's in there, if there are there holes, are there? I mean.
Yes.
Yeah.
Currents. Is there something? So Earth has this. Magnetic shield, so which protects us, right? And you could say, do these planets or do these moons have that? And what does that tell us about the evolution of the moon? And you can also talk about currents
to get there.
Yeah, of the waters underneath the ice shelves. So if they find there's liquid water, I think that is Europa, right?
Yeah.
Which has the ice shelves and the and underneath the running water. So there's a lot of these things. There's another mission which is not funded, which is called Moonraker, also looking to go to.
They're taking Roger Moore out? What's the Moonraker?
Yeah, I hoped to meet Roger Moore on that. But that's a similar idea, to go to these moons and investigate the magnetic field of these moons and do some spectrographic images. Of course, you always want a camera.
Right. You
helps
gotta
with
have
funding.
a camera. That's good. Yeah, that's true.
Yeah, have a camera. Yeah. I want the quantum sensor on it. You have a camera. We're good.
Right.
So there's all these kinds of different things that, so magnetic field sensing, definitely something that we're interested in. However, that again is more the Institute for Quantum Technologies. We are here very interested in acceleration. So both gravitational, anything that pulls us to Earth, anything that changes over time. So you can do that on ground and do local things like searching for water, which, if you think about it, water underground has a different density, and therefore produces a different gravitational field.
Oh wow! Mining
than
as well?
say
Use it for mining
rock.
as well?
You could use it for mining.
Not that
so
I want to
whenever
do
you
more
would want,
mining. I don't want to, but
no, there's a paper which talks about detecting rail tunnels for railways.
Oh,
So
yeah.
where you could see that aquifers are a big thing, and of course you could see how that, I spoke about it in the beginning, right? How that falls into protecting people from the impact of climate change. You want to detect where water is and help them build the wells at the correct points and help with water distribution and stuff like that. So this might be one aspect of these things. But you can also do that from orbit. So you can measure gravitational fields from orbit, and
that's
seems more of a
incredible
global
to
picture.
me that you can do that.
Yeah.
If you got to do all this stuff in a lab, sounds complicated. But then to put it into a little box and send it up and actually have it floating around is not floating, flying, whizzing along. Seems like a lot to go wrong.
And not to have anybody with it, right?
Yeah.
Like I told you before, I wanted to be an astronaut, and I told them I could help you.
I'll go up with it. I'll be there. I'll go as well.
I'll be there. I could help you repair or update.
Like, no, Lisa, you can't come along on the mission with the sensors. Someone's got to clean them. Yeah.
Yes. I could yes. I wanted to do all of that.
I just picture you trying to sneak into the launch with the
Yeah, you don't see me.
Dressed as a giant.
I don't know what you're talking about.
With just like a big fogging thing of liquid nitrogen, just to look like you're doing something really important. Yeah.
Exactly. Yeah, like a big bag over my head, and then just some vents for the.
I think she thinks she's dressed up as a photon. I don't. What is that? All right, I'm going to pull up the chat. I hope I'm not going to embarrass Agni at all. Here we go. Okay, Agni, all good. Most of the chat is getting their brains blown and talking. Okay. More than an hour in. Maybe it's time to address some of the viewer questions. Thank you, Agni. I knew you were going to say that. I didn't want to bring up the chat because it automatically moves us over on our stream.
Fine.
In fact, I should just double check that. But all right, here we go. We've got some questions. All right. Cerulean89 asks for more examples of how quantum mechanics is applied in real life, and asks casually, Sandra, how is quantum entanglement specifically being used? Okay, so start with that. Let's go with that. So how are we using quantum mechanics in our day-to-day? We talked about computer screens, although I'm not sure entirely how we use quantums for that. And also the MRI, I also don't know how they get used either, but I know that they're both being,
Yeah. I want to step into a different direction.
Please do.
Because we are using it every day to navigate.
Oh.
So GPS and GNSS basically have on board something which are called clocks. These are not
the clocks. I forgot about the clocks. Yeah.
These are not. We are currently developing the next generation and the generation after that. But even the ones that are currently in orbit, which are there are the masers, which is hydrogen, some hydrogen oscillations, and then there is the rubidium clocks. Basically, you might have stumbled across it. It's called a RAFS, and that's the rubidium radio frequency something. And so what you do is you take the rubidium, and you're doing exactly what we talked about before, but you're ignoring the shelves and the shelves. So you're just putting in this case, a radio frequency photon, not an optical, but a radio frequency photon. Same different. And you excite a state, and the state relapses. And you tune the laser until this excitation and relapse happens with most of the photons, with most of the atoms inside of your glass box.
Okay.
And this way, the laser that you have, or the radio frequency source that you have, is now, we call, stabilized to this box.
Okay.
Right? You have changed the frequency until it matches the box, and this means that this laser is going for a very long time, the radio frequency source is going for a very long time, be very, very stable on that specific frequency. And that sort of ticks away. It gives you a radio frequency signal, which is very reliable, and very
So it's a
constant.
radio frequency is basically what is now dictating, is now conducting whatever technologies you're using.
Yeah.
Yeah.
So, and that's in itself, I would call a quantum system. And the radio signal, you have the maser and you have some other things there, but in principle, the radio signal from that is sent down to your mobile phone.
Right.
And what the satellite does, it tells you, I am now. So because it has this ticking, it has a very precise time for itself, right?
Right.
It
right.
knows very well when it is.
Right.
Because it's so stable and so precise because it's tuned to this rubidium cell. So it basically just tells you, I am now. If you, on your side, also have a radio frequency system, which also tells you, I am now, you can now know the difference, the distance in time between the now that the satellite had, that traveled down, and your now. And that will give you a spatial distance.
Yeah.
So now you have a spatial distance around that satellite where you have to be. If you put in a second one, these two spheres basically become a circle. And if you have a third one, the circle with Earth ideally becomes a point. And now none of us in our phones have a rubidium oscillator.
Damn.
You need a fourth one to get the time signal. So by having 4 satellites tell you, I am now, you can produce your position.
Yeah.
And this is one application of quantum mechanics in the real world at this moment in time. And we are developing with optics. So we'll replace the radio frequency source with a laser, and then you replace...
Comes even smaller.
Yeah.
So the smaller it is, the more precise.
Exactly. And then you can reduce the motion of the rubidium. So you can produce a magneto-optical as a molasses or a Bose-Einstein condensate, as we talked before. You cool them, which reduces the bandwidth of the shelves. Now you have to hit it even more precisely.
Wow, which makes
so
it
the
even more...
laser.
Wow.
Exactly, and that way you can do positioning even more accurate, or transmit time to the world even more precisely.
So you're going to get to the point where it's like, oh, you moved, like where even any tiny little movement. Wow. From space.
At this time with these clocks, if you have them on ground and you pull them a centimeter off the ground, you can measure that distance.
Wow.
So you can, just by the change in the frequency because of the gravitational field and special relativity, you can, this is the level of accuracy that we have.
Oh my God, that's amazing. That's, whew.
So
that,
I hope that helps.
Yeah, that's
with
fantastic.
A real life application.
Absolutely, there's a real life application. I love it. That's fantastic, and one that we wouldn't have even thought of. All right, what else we got?
Yeah.
What else we got? Casually Sandra says, how is quantum entanglement specifically, is it being used right now?
Yes, of course. So we are not in the same way using it right now. We are thinking about using it. And there are basically 2 big applications that we're thinking about, and we basically talked about both of them.
Right.
One is to generate quantum keys, quantum secure encryption methods, and do that. There's some commercial applications, so some commercial products at the moment, but it's still very low and it's just rising and it's coming and things are going to come. This is one. And the other one is the quantum computing.
Right. That's and the entanglement is required for both of those. Is there anything else?
It's required for both of those.
Anything else it's required for? Do you think of?
The entanglement?
Yeah.
There are some ideas of testing all sorts of stuff. People get very creative if you want to ask them, so you can.
But there's no big push for it right now.
No.
Okay.
No, there's so of course we want to again investigate the limits of quantum mechanics using entanglement because so the idea people have tested that. The original idea was by separating the 2 detectors even further and further out. At some point, they expected that the wave function would collapse before it reached the detectors.
Right.
And then you would not measure the entanglement anymore. You would not measure the quantum state, and you would fall down. And so people have enlarged the distance.
To reach a certain point is with the assumption.
Yes, it would fail. It doesn't. So they tried it. I think one of the first ones
which is way cooler, by the way. Way cooler that it doesn't. Yeah.
Yeah, so there was an Erlangen where they tried it between buildings. Then the group of Zeilinger, they had, I mean, the poor PhD students, they sent them to the Canary Islands to send it between the Canary Islands.
Boy, that's tough.
It's
Job,
I mean,
huh?
hard
Man.
life,
Yeah.
hard job.
You sign up for that
Yeah.
instead of trying to fling yourself into space. That's what you gotta, you know.
Yeah. No. And then the Chinese
Yeah.
have managed to do it from ground to space.
Oh, wow.
Onto a satellite. Still nothing. There is a proposal by NASA.
So it
to
still
do it
works
to the
fine.
moon.
You change one,
Still works
the other
fine.
changes right away.
Yep.
Wow.
Yep.
Okay.
Still works fine. There is a proposal to do it to the moon. You will get into signal intensity issues there, but there might be some other things. So maybe the gravitational field might impact the frequency and blah blah blah.
Yeah, right. So it may seem like it's collapsed, but it hasn't because there's just other mitigating.
There's other things,
right.
and of course, if you understand these collapse processes, you can then again do the bug it's a feature thing and try to detect it the other way around.
Oh yeah.
But that is maybe a bit further out. So
Right.
that's not something that I would.
All right. So quantum computers and quantum keys basically are the big.
Yes.
Now, and when they talk about quantum keys, that is quantum communications now. When they talk about wraps it all up.
Generally.
Basically. Okay. All right.
Generally, yes.
Fantastic. All right. I'm going to go back and see what else we've got. Now, we have kept you for an insane amount of time. Are you okay with some questions?
I am happy.
Okay, I'm happy.
I'm happy to.
Poor Agnes did not sign up for the entire day, I'm sure.
As soon as the chat doesn't want any questions anymore,
there you go.
then I'll lay down and cry for a bit. But until then, I'm happy.
Kenny Ken has got the question. This is the $60 million question, which is, how do particles know that they've been seen? And I think if we can answer that, we would be very, very famous.
We would be. And so I don't have a nice answer for you there. And seen basically also means by an electric field or a photodetector or something. I don't know. It's the wave function that collapses.
It's bizarre, isn't it?
I don't know. I don't have a good answer for you. I can only encourage you to go into quantum mechanics, study it, go and find a fun group to do these things with, and search for your answer that satisfies you in that, because I have accepted that I don't understand it.
What does one do? Like I'm getting the sense this isn't something you could just sort of do in your garage or something. Like, I mean, are there quantum mechanics or physics or communications groups that one can join? I mean, is it like the biohacking community? Is there a quantum hacking community? Can this be done at home?
Yes. So there's. I don't know about at home. But
how about in a garage?
Potentially. I mean, there's nothing that should stop you from building an electron gun and a double slit, and you would have a perfect double slit experiment, and then you put a plate beneath. So a double slit is basically what it sounds like. It's a plate, and it has two slits in it, and my fingers can't put that together, but you have two slits in a plate, and these will produce an interferogram behind it, similar to what happens if you put two stones into water and you get these rings, and where they overlap, you get these fun sort of patterns.
The double slit experiment is something that everyone should look at if they want to understand, or even try to understand quantum mechanics. In fact, was it Feynman who said that this is the one? If you understand this, you basically have quantum mechanics.
If he did, he was right.
Okay, right.
So it's super unintuitive.
He also played the bongos though too, and
he also played the bongos. I mean, it's
seems weird to
one
me,
or the other.
Hippies.
One or the other. I mean, you can also try to play the bongos in your garage and see where that gets you. But
I'd rather have I prefer the electron gun, but but the electron gun is basically just just the old televisions, isn't that the?
Yes.
Yeah.
Yeah.
Okay.
Yeah. So you could basically use an old television. A very good example. Very good idea. Use the old television. Take that out, and just shoot the electrons at a double slit, and then you need something to detect them with. So you reuse your television screen and put that behind it, and then you should see the different stripes in different areas, and then you have yourself a meta-wave experiment, because this can only explain if you go into if you explain the electrons as waves and no longer as particles. And then if you want to confuse yourself, you take a charged plate and put it behind one slit, not behind both, but behind one slit. And your interference pattern will vanish.
Disappears.
And
as if the particle had gone. Yeah.
because you generate what is called a which path information. The electron now retrospectively has to decide through which slit it went.
Oh, a witch. I was thinking like witch, like with a little pointy hat, but no, I see. You're saying
no,
witch
no.
slit.
Yeah.
Okay, got it. Yeah. Got it.
German accent, it's horrible.
Yeah. No. There's no
which,
different way of saying it. That's Okay.
Which path information, and then you can work out whether that is your answer. Other than that, I suggest to go and try to join one of the groups that do it. So Marcus Arndt in Vienna would be one, or Marcus Aspelmeyer also Vienna, or
I have to go to Vienna
in the UK.
There you go.
Yes,
more than happy
it's
with
mandatory.
That. And the UK as well? Yeah, of course.
Yeah, there are some groups in the UK, there are some groups in the US. There are different groups all around the world that study both on entanglement and on high mass interferometry. That is where this ultimately goes. So you want to increase the mass.
We have a quantum computing company up here called D-Wave, which is I think the Canadian contribution to.
Yes.
Yeah. What does that look?
Yeah.
D-Wave
is a bit of a controversial topic, I think.
Oh, is it really?
Community.
Oh, okay.
Yeah.
All right. Okay.
Yeah. They were one of the first ones to have a quantum computer, and nobody believed them, I think is what happened there.
So there's a hard time proving what they discovered?
Yes. Yeah. And I sort of carried that over. I don't know if this is substantiated.
Yeah. No, that's fine. I just
know.
Yeah. I just saw Canadians.
I know. Yeah, they are.
You never trust those Canadians, anyways. Come on, Canadians.
No, they are in the game. They are very important in the game, and I'm sure that there are some things. But yes, if this is your question, go ahead, find yourself a research group or a good book. And,
well, that was actually my question from Ken. Kenny just wanted to know how we know that they've been seen. But as you say, we have to figure that out. Great. Raging Pixel asks, what would happen, or it mean, if we can actually determine and control the split of the photons?
I guess that was for the beam splitter. So the split of the photon it's very much a beam splitter sort of thing. So it's a special crystal that you use, and what that means is basically that the energy that you put in is now diverted into two paths. Okay. You could think of, if you wanted to, so I've got a bottle of water here, so I'm going to give you a water analogy. If you run a water and you have like a divider, a physical divider in the middle, and then you generate two streams. So there's no real secret in that. This is just the absorption of the crystal and then the crystal re-emitting two photons.
Right. Okay.
There's no...
Right. There's no magic.
No real secret.
Okay.
There's no magic there. I mean, there's no magic in quantum mechanics as such, but there's no real...
So you say. But there's witches.
Yes. There's witches and cool guys. Something is off.
You got teenage witches. It's like Bewitched or something. All right.
Something is off.
All right. Maxger 099 asks SG1 question. What? No, SG1 questions? How are you going to answer that?
No.
He doesn't watch them.
No. Well, we shouldn't.
What do we got? About quantum physics and complex consciousness. How? Whoa, okay. Okay, Yukonai and Megalomaniac asks about quantum physics and complex consciousness. How are they related? What is your opinion, Lisa, and what are the general thoughts about it among quantum scientists?
That sort of sounds a question towards the quantum biology that we, or quantum... I'm a bit cautious about saying quantum medicine because there is a lot of hoax surrounding that.
Yeah.
There's a lot of people out there who use that and talk about, I don't know, waves and stuff and crystal healing, and from a quantum physics point of view, all of this is nonsense. There's not, if that helps you, all the better, all the power to you. But
there was
none of that works.
There was a wonderful book that I read, which again, there were parts of where I was going like, is this proven? Is this not? Basically talking about things like, the potential quantum link between birds being able to direct themselves like they shouldn't be able to experience these magnetic fields unless they had some kind of a quantum effect happening in their brains or something. So,
there's truth to that.
Well, there you go.
There's
See, that's
truth
and that was
truth to that.
And in the book they seem to explain it that they didn't say this is the case. They just sort of said, is it possible that there is a quantum biology in effect?
There's truth to that. So I did not follow up on that. I remember that they put birds into cages to shield them from magnetic fields so that they couldn't navigate along the magnetic
Mm.
field. And dogs or wolf or foxes seem to do the same, like attack along north-south direction or something of that
Right.
sort. And frogs seem to do a similar thing.
Trying to find the
When
title
I
of the
was
book
in
while you're
Vienna,
doing-
when I was in Vienna, one guy from our group, in the end unsuccessfully, tried to figure out if bees and wasps would have some of these quantum properties. I don't remember how he did it, but there is some truth to that, right? And as we said in the beginning, there's these tunneling effects which could explain how neurons interact and stuff like that. So
Right.
that definitely is
when
something.
you get that small, I mean, you were talking about firing viruses through the double slit experiment.
Yes. Yeah. So there is a part of that is definitely true. Now, I am not a biologist and I'm not a medical professional.
Right.
So all I can talk to is mechanisms that might work in that direction, such as the tunneling effect, which could explain how distances have reached in the brain to have neurons interact. So this is something that I could. No worries. No worries. I keep talking,
No, I found the name of the book. So the book is called Life on the Edge, and it's a fascinating. If people are interested in looking into this kind of stuff, again, I can't speak. I don't understand enough about it to, obviously, I just play Brilliant on television. But that was a fun read for me because it got me thinking about this whole thing. And then there was a recent study again with those tryptophan tubes that was kind of fascinating as well.
Tryptophan is a very nice molecule. You
just
can
thought
do
it was
all kinds of
turkeys.
fun.
I just thought it was a turkey thing. I didn't know it was all fancy.
Yeah, no, it's fun. Yeah, you can do it. There is some phthalocyanine is also one of these fun things that are easy to handle. Hard to say, but easy to handle because they nicely fluoresce and do all the things. They're very stable. They do all the things you want them to.
Yeah, I had no idea. I was always just blaming it for being tired after my Thanksgiving dinner. But little did I know it was a whole quantum thing going on. All right.
Yeah. So I guess the answer is probably, but I'm not deep enough in the consciousness and metaphysics part to really say anything to that.
Okay. Fair enough. Okay. So we've got quantum condensates. Okay. We've already asked. Gimpy G already to the front. Okay. How would the sensors on? Okay. So this is KZ Howell asks. How would the sensors on the JUICE mission? I'm so excited about this one. I got so much cool stuff happening.
Me too.
Distinguish between the intense radiation and gravitational field of Jupiter and that of the target moon.
Yes.
So this is a lot of interference.
There's a lot of interference. So the fun things with that is that it is not the primary measurement instrument. What it is there for is because it's got a fun and interesting property, and that is so-called drift freeness. So normal magnetometers, Hall sensors, or flux gate magnetometers usually work on some sort of a coil that is wrapped around them, or some solid state system that is then electrically probed. And these systems, if they experience, or magnets, and if these systems experience magnetic field, that can lead to a change in the sensor.
Right.
Which
like a permanent
means that
change?
a permanent change, which leads to a drift of the sensor in time.
Oh, okay. Right.
That happens to magnets a lot. So if you have a magnet and you expose that to a stronger magnet, or if you have a piece of iron that is non-magnetic or doesn't act magnetic, and you expose it to a very strong magnet, then it will start acting magnetic.
I know it. A lot of my screwdrivers. Yep.
There you go.
Yep.
And so the same thing can happen to, I want to call them classical magnetometers. And the rubidium cell does not suffer from such effects. So they are there to calibrate the other magnetometers, which means that you measure the magnetic field, and you tell the other one, no, it has to be, you have to correct yourself. You're drifting off. This is still constant.
Oh, interesting.
And the other ones, so the rubidium system, as far as I understand it, cannot measure a vector field, which means it can only tell you a scalar. So scalar and vector, basically a vector is something with an arrow on it.
Right.
It tells you this is the direction the field comes from.
Right.
And a scalar basically just tells you I don't know where it came from, but it's 15.
Right. Okay. All right.
And the other one says, right, so the other one tells you, yes, it's 15, but it's in that direction. And so the other ones do the vector measurements, and this one just does the scalar to correct for those.
So they just fix each other, basically.
Yes, they fix each other. However, there are some, as I said, in V-centers, for instance, they are capable of doing vector measurements. And as such, if you put a NV-center to Jupiter and its moon, you would be able to tell
the diamonds with the
exactly
yeah.
with the holes in it. If you put an NV-center to one of the moons, holy diamonds. Yeah. Diamonds are a girl's best friend.
There you go. Yeah, and quantum physicist's best friend too, by the sound of it. So yeah.
I mean, I think that's what they're saying, right? That girls are quantum physicists. I think that's what
it should be.
Is.
Yeah, by the sound of it. Yeah.
Yes.
Yeah. You're doing a good job.
Yeah,
so I mean, I'm assuming that yeah.
So here we are. So the if you can tell the direction from where it's coming from, then you can also tell. Then you can also differentiate between the moon and the Jupiter itself. Also, you can do some calibration measurements by when you approach, you will see the one field stronger than the other and stuff, and so by that you will be able to differentiate.
So you're just making sure you've got lots of different ins for this stuff, so that you can have the various different instruments adjust based on what the other instruments are telling them.
And then also, the closer you are to the target, the more you will realize the field of that system. So if you're very close to the moon, then you will be able to tell that this is the system that has to excrete the magnetic field, or has to extrude the magnetic field, and so this is what I'm measuring. Magnetic fields, I think,
So the stronger it is, the easier it is for the sensor to be adjusted to it. Okay.
The closer you are to the source of what you're trying to measure, the easier things are.
Makes sense.
And so that's another one. And I lost my point there. But yeah, so that's basically how you will be able to differentiate between the two. You can also do something with shielding. And so I think magnetic fields decline with an R to the 4 or something. R squared? Or...
Are you asking me to correct? Because I don't think I'll jump in.
No, don't worry. But there's a dependency of the distance.
Right.
Yes, there's a dependency on the distance, and so the further away you are, and then if you, in addition, have an idea of the direction that the magnetic field comes from, you will be able to.
Oh, right.
Measure.
Okay, so you go. Okay, so the moon's over there now, and we can check that effect and go. Okay, great. Now we're measuring that one. I see. Okay. All right. Oh, that's great. Okay.
Yeah.
So hopefully that answers the question.
Yes. And you could also do something about frequencies. So if you have something that changes, you will be able to see a certain frequency, and stuff like that. So if you have a rotating planet like Earth, if Earth were to rotate by your system, then the change from the magnetic south to the magnetic north pole, you would see like a certain frequency of that, right? And so based off of that frequency, you could also tell which body you're looking at.
Wow.
Because if it's smaller or rotating faster, stuff like that. I
never would have thought it'd be so complicated, just that portion of it. Just like, how do you know what, because again, it's not like eyes, ears, and you can't reach out and go like, oh, there it is. I mean, it's all data, basically. You just got to, it's a lot of numbers.
Your eyes and ears are also just taping data. Your brain is just very, very capable of distinguishing what is happening and what's coming from, and this is why you don't see your nose and stuff like that. But that's a bit.
I see my eyebrows sometimes, but that's only when they grow really long. Sometimes I get them in the corner of my eyes. Yeah.
But you can try to see your nose, and then when you really try, you can see it, and then at some point, if you don't pay any attention anymore, it's gone.
It's gone again.
And that's sort of it's sort of the frequency effect, right? Your eyes say, that's there all the time. I don't have to worry about that. That's perfectly great.
I read this wonderful book called The Deceptive Mind, which is all about critical thinking. And one of the big things about the critical thinking stuff is just the bias, all these weird little biases and things, and that we are literally just processing electrical information. So we're not seeing it. I mean, it's fascinating. I mean, and even that is still not as weird as this quantum stuff. All right, we got a couple. I'm going to do a couple more questions, and I'm going to let you go because we have been, holy moly, we've been going for like 2 hours.
I know.
I know I could do this all day, every day. Lisa, you're like the best. I love this. Absolutely.
No, we're going to bore all the people on the chat.
So I don't think so.
But yes,
we still got questions. As of 2:00, there were still questions coming in. So, Jen, asks for Lisa's thoughts on the idea that during the initial, during the initial singularity, pre-Big Bang, quantum physics was the ruling physics. So it influenced back then everything that exists on a macro scale now.
Oh, well.
Boy, how's that for a little question?
Yeah, so here it goes. From my understanding and my picture of the world, there is no pre-Big Bang.
Okay.
The Big Bang, if you're going into how Einstein described the world, he basically says it's a four number vector. So
right.
We usually talk about 3 dimensions x, y, z, and he said that the 4th dimension, time, has to always be viewed in that vector. So we're talking about 4-dimensional vectors at all times. And if you think that through, in the end, you come to a point where you say the Big Bang itself has to be the origin of time, which is nicely echoed in things like Greek mythology and stuff. So from my point of view, it's very difficult to talk about anything that is pre-Big Bang. And then, even though I studied high energy physics for a while, it's still difficult for, I think, the world of physics to say what happens 10 to the minus 10 seconds after the Big Bang.
Right.
So this might sound like a small amount of time, but there's so much happening that this is a crucial amount of time, even though it's short. And if I can't even tell you what happened after the Big Bang, from all the observations that I have, I will not be able to tell you anything about it, what happened before. There are some ideas about D-branes in the 20-something dimension that caused the Big Bang and stuff like that. Yes. And this goes into some directions where particle physicists try to explain what happened. And that's a very valiant effort, and they try to do all these things, and there's these particle accelerators, and we're very curious, and this is an important question. It's just not mine.
Right.
So I don't know. And then after that, there's a lot of plasma physics and stuff, and fun things, and high energy physics, and quantum mechanics comes to or is observable at a very much later stage.
But someone has some kind of a theory that it was all quantum, and then the universe began type thing?
Then the universe began type thing is a tricky one, because it would all be after the Big Bang. So the universe began, and then that was quantum mechanics.
Yeah, I can't get my head around it.
And I'm not too sure about that. So as far as I understand,
there is
there's some quark gluon plasma and stuff like that, and that goes, it's all over the place in and of itself.
Okay, all right. So not really Lisa's area of expertise for this. Not buying that so much. James Argurney, he's great. He's
okay.
He's my my little virus friend, I would say. He works with phages out of University of Georgia, I believe it is. But anyways, James always has good questions. All right, have you read What is Life? Schrodinger's suggested that by understanding heredity, we might find a new type of physics. We didn't. But do you think that it might hold true for, say, consciousness? Ooh, everyone wants to know about this quantum consciousness stuff.
I guess that's because it's I read a quote that said basically the universe is an ongoing explosion, and sometimes the universe explodes so hard that it starts thinking about itself. And I think there's a lot of truth.
Who said that? That was great.
I don't know. I found it somewhere.
Oh, that's good. Okay, all right.
You find it somewhere on the internet. Yeah. Probably somewhere on Instagram or Facebook or whatever. And so the question of consciousness is an important one for us, because we have it. Clearly, we think we have it. Maybe some alien civilization might think we're just ants, but that's totally besides the point. We have it, and the question, of course, how comes that a clump of elements produce something that in the end can start thinking about gravity and magnetic fields and quantum physics and high energy physics and the Big Bang and so on and so forth, and relationships and love and sadness and all the complicated things that govern our lives. So I understand these questions, I just can't answer them.
But you said earlier that it's like you had a sneaking suspicion that there's definitely quantum stuff happening in there somewhere.
Yes. So the brain, but that's sort of again, separating out the two, right? This is more on the elements, how I understand how elements bond together and how DNA and RNA forms. What I can't do is from how a string of DNA forms to this now reproduces. This is weird, and how the reproduced thing then gets to consciousness. So what I can allude to is that I think that processes in the brain can be governed by quantum mechanics, or it's, as from what I understand, this is the truth. The quantum mechanics explains a lot of the processes.
If it's operating at that level all the time anyways, then surely it's got something to do with, right, yeah, okay.
Yes, yeah. So that's definitely happening. But that is more of a how than a why. So I don't know how, from a tunneling effect, we finally come to madly falling in love with your favorite TV character. That's that's and how heartbreak comes from that, and how the idea of quantum mechanics comes from that. I'm out there.
And I think it's also, I think there's a danger here with quantum, and you see this a lot with sci-fi films and books and stuff, where quantum becomes the god in the gaps. You know what I mean? Like, it's like all of a sudden it's like, oh, it's a quantum thing, and that just somehow that's supposed to just explain everything. Like, there's a, you know, it's so tempting to go like, we've got it. The spark of life is actually a quantum phenomenon, and we just haven't found it yet, type thing. So.
Yes, and that's
makes great sci-fi though.
Makes great sci-fi. Makes great sci-fi. Makes me not too happy with a lot of sci-fi, but that's again a different. As you say, it's if you don't really want to explain, you say, this is this quantum thing, and then you
we
have
do that all the time.
This ball of light, and I'm looking at it like, where's the electronics, and do you have a laser, and
activate the artificial gravity. I always love that one too. That was, so yeah.
Yes. And there's actually, to just finish that thought, there's a big issue that arises with that. There in Germany, I watched a documentary about something that is called the Healy, and the Healy claimed to be a quantum medicine device, and turned out all it was a transistor, which technically is a quantum device, but it couldn't do anything. So there's a lot of that stuff which in movies is fun and easy, and I can I can be an asshole and arrogant about it and say I don't like movies because they use quantum, but that's in the end that's harmless. But there's a rather harmful side to that, where these things are used on people who think that this is the end goal because it sounds so amazing and magic and whatnot, and to prey on these people, and none of us is immune to that. Pseudoscience, and I'm not immune to that either, right? It's just quantum mechanics that I will probably question, but if I were in any other field, I might be falling into that trap. So there's some problems.
There was a wonderful thing I was listening to the other day. Actually, it was at the cybersecurity conference. I was just at the cybersecurity conference in Toronto, and the keynote there was saying that if someone's selling you something, if someone is telling you something, find out what they're selling. Because once you know what they're selling, so if someone's saying, "Oh my God, vaccines are terrible, don't take them," the governments are implanting Bill Gates tracking devices, and they're selling you supplements, then chances are that it's not that legit. So, I think that's it. I think that's it for the questions. Agni, are we? I think that. Yeah, I mean, Agni's probably has probably gone and lived her life at this time, but I think I should let you go because you've been absolutely amazing, and I kind of want to invite you back, and I'd like you to say yes as opposed to having to, take your entire day every time. This has just been amazing. I'm going to ask you one more question if you don't mind, just because it's one of my sort of favorite ones. How did you get into this? What do you think it was going forward, in your life that made you, want to become a quantum physicist?
Very much the question that we had before, like how do the particles know that they've been seen? For me, it was there's a book by Hawking, and he talks about high mass interference, and I listened to it and I was like, prove it to me, and I still won't believe it. This is no. I can't get this in my brain. How on earth the particle interferes with itself, and if I observe it behind, it all breaks down. How? What? No. Wait. No. No. I understand it on paper, but my experimental physicist brain doesn't accept it. I don't understand it. It's not. And that led me to go and be a masochist and say, I want to at least know what I'm so worked up about and how that actually looks in a lab. And I want to try it. And I want to be involved in that. And this is what got me here.
So wait a second. So your brain exploded and you started thinking. You've just proved it.
Yes. But it still baffles me, as we figured out throughout this talk. It still baffles me, but I love it. I love it every day. And it gives me so much joy to talk about it, as you see. And I'm so grateful for the opportunity.
That. I mean, that's what I find so exciting about it, is that I see just how, I mean, it seems overwhelmingly complex, but the fact that you get so much joy out of this it's like palpable. I love it. Like it gets me excited about it. So that's and what do you need to do this? Like to do what you're doing? I'm guessing math is going to be important.
No, in the end, not that much.
Is that a foundation? Okay.
So there's a lot of math involved, but we have in the Institute in Ulm, we have a full department which is filled with theoretical physicists. This is also something to encourage people to learn it. Yes, there's no way of getting around math. But math is not bad. It's just numbers on paper. You can be cruel to them if you want to. You can light it on fire, and I mean, they will scream and haunt you a bit. But here we are. There's no. You don't have to be scared of them.
The cruelest math classes I've ever been to.
Yeah. Then they lit it on fire. It was weird, but we danced around it, and it was fun. So this is one part of it. Of course, you have to learn the math to understand where you're going with it and what is happening. But in the doing, you don't. So in the doing, you're really there to harness the phenomena, to break it down, to understand it, to make it work, to give it the magnetic shielding or the not magnetic shielding, or all these kind of things. So math is not that much of my day-to-day.
There's still a fair amount of practical stuff involved as well then? So there's actual hands-on stuff you can be doing as well?
There's actual hands-on stuff, but now that I've gone into the position that I'm in, so I didn't say that in the beginning, but I'm now head of this institute together with my colleague. So for me, it's a lot of telecom conferences and talking to people and getting others excited about the stuff that we have and trying to sell my things. So I'm also here selling my stuff. So in case all classicals is bad, please buy my quantum stuff. No, but yes, so we're trying to bring it to the world.
And how is this funded? How is your institute funded? Is it a government organization? Is it how's it?
Yes.
Yeah.
We're primarily governmental funded. Of course, we're always looking for third-party funding. That could be governmental funded again. So there's some government funds from the European Union, from ESA, from Germany. There's different ways that we can get money to do our research. And then there are industrial contracts where we develop something very specific for a company or together with a company. So these things exist as well, where we get money from the private sector.
There's got to be a lot of that. Surely there's a lot of development in that, because with financial and there's got to be quantum computing, all that kind of stuff is.
Yeah, there's a lot of private investment in these things, and still also a lot of governmental funding in these kind of things.
And you have to oversee all of that.
Ideally, yes. There are things that I'm missing, as per usual.
So you've got to be in two places at the same time as well, then, all the time. You're like, you are
I'm
the
in an
quantum queen.
entangled state.
Yeah.
There you go. I guess I have to accept that, but so that's my day to day.
Don't fight
and,
it.
I won't. I try not to. Yeah. And then, I hope that I will be allowed to go to one of the labs sometimes and.
Yeah, it's got to be fun to get back in the lab and play with.
Gets me so excited. Every time, whenever I'm anywhere with a lab, I just love it so much. Labs are the best.
Yeah. It's fantastic. Well, look, I cannot thank you enough for you've just talked quantum mechanics with us for 2.5 hours.
Yes.
Yeah, I cannot thank you enough. And I could keep going, but we don't have any more questions. I'll respect that. And we've only just scratched the surface. There's a ton of other stuff. I'd love to hear, about some of the more specifically some of the stuff that, the new projects you've got coming up and the things you're interested in looking forward to in the future. And so I'd love to have you back at some point if we can, if I dare.
Absolutely.
Of course, I ask you while we're online, so you can't say no. That's
no, I can't say no, Ryan. It's like getting the proposal while you're on screen at the
yeah, that's right.
stadium.
That's right. Too soon. Yeah.
No.
Way too soon.
Right. No. So again, thank you so much. I love talking about this stuff. You can see that I don't want to stop talking about it. I really enjoy it. I'm super excited right now. So yes, of course, I'm happy to be back. I'm so grateful for you to invite me. I'm so grateful for Agne to get the contact.
Yeah, thank you, Agne, for putting this together.
It's been fun.
Yeah, it's been fantastic. All right, well then I will wrap it up. I'll say until we geek again, I will say be kind, be brave, be brilliant, and we'll talk again soon. Thanks, everyone. Appreciate it. Thanks for all the questions. Thanks for joining us. Cheers. All right, I'm going to